It's a real pleasure to be back at the IoA, even if it's virtual. I try to visit Cambridge every few years, usually in the summer. So I miss term time, and most people are out on holiday. So it's a pleasure to be with you, even virtually. It's hard to believe that it's coming up on 10 years since I left the IFA, and so it's a pleasure to be able to share some of the work that I've been up to over the past 10 years in studying the obscured universe. And today in particular, I will be focusing on what there is to learn about dust obscured galaxies beyond redshift 3 or 4, so between redshift 3 and 8 roughly, where there's not a lot that's known. And so we've had recent efforts of the past few years to really learn much more about this epoch. And yeah, so to begin, I want to first zoom out and give a broader motivation for those of you who particularly are further afield from extragalactic work or understanding of dust in the universe. The overall spectrum of the universe, I love this plot. It's really a gorgeous plot from Riley Hill's 2018 paper showing the integrated spectrum of the universe from the radio through to gamma rays. And of course, the CMB dominates the energy budget of the spectrum of the universe overall, and has a nearly perfect black body. But second in energy contributions to the spectrum are the peaks in the infrared and also the optical background. And you'll notice that those are roughly equal peaks, and everything else in terms of the energy budget is rather low. And the optical background we've come to know very well from studies over the past 100 years from telescopes that operate at optical wavelengths and into the near infrared. That is, to 0th order integrated starlight of all galaxies in the universe. And the cosmic infrared background is less well constrained and less well understood, but to 0th order, it's understood to be the reprocessed dust emission of that starlight on extragalactic scales, so looking at galaxies out to very high redshifts. And if we look at the baryonic budget of galaxies overall, to 0th order, you can say, stars make up often the lion's share of certainly the light, and often the lion's share of baryonic mass in many galaxies. And if you were to plot the schematic of the spectral energy distribution of all of the light of stars, then you would see something like this. It's just the aggregate black bodies co-added of stellar populations. So you have a contribution from ionizing stars, of course, O and B stars, and then non-ionizing stars. And depending on the type of galaxy you're looking at, these stars may make up 30 to 90% of the baryonic budget in terms of mass. Of course, gas is also present in galaxies at a wide range of gas fractions, depending again on the type of galaxy you're looking at. And this gas lives in a variety of environments, from H2 regions to molecular clouds and neutral gas clouds on different scales and different densities. And the emission mechanisms of that gas is often through these discrete emission lines, and also free emission underline the discrete emission lines. Of course, many of these features we can see in the rest frame optical, like H-alpha and the Balmer series and Passion series into the near infrared. But of course, there are a suite of lines that are emitted at longer wavelengths as well in the rest frame far infrared and into the millimeter. And dust is a funny thing. In terms of the baryonic budget of galaxies, it's negligible. Typical gas to dust ratios, of course, are 1 to 100, or 100 to 1, rather, gas to dust. And yet, despite this negligible amount of mass, trapped in dust grains in the interstellar medium, dust can have a really profound effect on the observed characteristics of galaxies' spectra. Shown here, dust can of course, efficiently absorb radiation at rest frame UV wavelengths on into the optical via the well-characterized dust attenuation curve. And where does that energy end up? It's absorbed by the dust and re-radiated at longer wavelengths. And what is the bulk of emission here is a cold, thermal emission, with kind of a diminishing power law of hotter dust temperatures towards that are more closely irradiated by the rest frame UV sources. So this is primarily cold dust in the ISM, peaking around 100 microns, temperatures of 30 Kelvin or so. And so what you're left with is, for this typical cartoon of a galaxy's SED, to zeroth order, you have two peaks with equal luminosity in both stars, stellar emission, and obscured emission. And this should be rather reminiscent of what we see in extragalactic background light, the spectrum of the universe overall, where we see a peak in the cosmic optical background and another peak in the cosmic infrared background. So perhaps this is a very simple explanation of the origins of the CIB, but of course it's more complicated than that, in that not all galaxies are equal, which is perhaps stating the obvious. But obscured emission can range anywhere from between 0 and 100% of galaxies' total, light that's reprocessed by dust. And that is, of course, dependent on the mass of the galaxy, whether or not there's ongoing star formation, and the geometry of the dust in galaxies, if it is indeed there. So this is a plot from Kate Whitaker's 2017 paper in which we collated data on galaxies out to redshift 3.5 or so, and studied what fraction of their total star formation is reprocessed by dust. So these are star-forming galaxies, not quiescent galaxies. And found that as a function of stellar mass, you see more or less this clean relationship, albeit with quite a bit of scatter, but the relationship itself doesn't seem to evolve out to redshift 3.5 or so. So at low stellar masses, a very small of the total star formation rate in galaxies is reprocessed by dust. So what we're talking about here is dwarf galaxies, which of course are of quite a bit of interest lately for various reasons. And I think it's safe to say that the most dwarf galaxies have very little dust, and so it's not something at the forefront of the minds of those who work on dwarf galaxies. But of course, they're not necessarily dust-free. Of course, we by virtue of being very close to the SMC and LMC, we benefit from detailed studies of the dust attenuation curve in these systems, and have hints that actually the dust composition in these galaxies could be quite different than even the Milky Way. If we scale up and look at slightly higher stellar masses, we're talking about systems like our own Milky Way. If viewed from afar, it would appear moderately obscured, and you might think, well, 90% obscuration is not moderate, but it falls into the category that many distant Lyman break galaxies fall, whereas, while we can easily see them via their unobscured emission, Overall, we think they're roughly, 80%, 80 to 90% obscured by dust. So far, what we know from the local universe is that dust composition may vary substantially across these environments and is quite complex. And that may be attributable to a different mix of silicate and carbonaceous grains. I won't get into the details of dust composition arguments in this talk, because I think there's much to settle before we can really understand the nature of the physics of the dust itself. And then at the very high mass end, this is where I focused primarily, over the past 10 years in looking at galaxies that by their very nature are massive, but we find that as a byproduct of being massive and also having ongoing star formation, something like 95 to 100% of their ongoing star formation signal has been reprocessed by dust. So with an increased SFR, you get a higher generation of dust mass forming through stellar remnants and AGB stars, and thus you end up with a more highly obscured environment with very complex geometries in some cases caused by major mergers, but also gas-rich disks can also harbor such highly obscured star formation. And I'll use the term dusty star-forming galaxy, or DSFG, throughout the rest of the talk to refer to this class of massive star-forming galaxies that typically have star formation rates in excess of 100 solar masses per year or thereabouts. And yet, despite this wide range of environments, I would say it's pretty safe to say that our understanding of galaxy evolution, particularly at early times, rests solely on our understanding of Lyman break galaxies, of galaxies that we found in deep pencil beam surveys with Hubble Space Telescope and other deep ground-based imaging surveys. That is rather limiting. If we're focusing in on a narrow dynamic range of galaxies, we're not getting the full picture of what's happening, particularly beyond a redshift 4 out to redshift 8 or so. So you might say, well, there has been a tremendous advancement in this field, and that's very true. Due to the commissioning and now full operations of the Atacama Large Millimeter Array, which has transformed our ability to study the obscured universe at early epochs. And just to give you a smattering of the impact of ALMA on extragalactic science, I wanted to share some of the key results as I think of them from ALMA in the past decade. We've been able to resolve ISM kinematics in individual galaxies out towards very high redshifts. This is the Ring of Fire, known as SDP81. It's a strong gravitationally lensed system at redshift 3.8, I believe. And by getting such exquisitely high resolution imaging, we are able to study the ISM in that host galaxy, but also through a detailed study of the dust continuum imaging, study the dark matter substructure of the foreground lens. We've detected tidal tails in galaxy mergers out beyond a redshift of 4, something that's quite impossible to do in starlight beyond a redshift 2 or so. And we see the tidal tails in dust. So this is a system at redshift 4.6. There are signatures of molecular outflows seen at redshift of 5. These are very hard to, there's a big gap in that we haven't seen these, beyond the local universe. And then, again, we see them out at very high redshifts just due to atmospheric transmission issues. We see examples of galaxies that are expelling gas at rates of 800 kilometers per second or so. Damped Lyman alpha systems. Galaxies previously only seen in absorption have now been detected in emission by the cold molecular gas. We've confirmed the existence of massive dusty star-forming galaxies out to redshift 7 or so. So the system has over 1 billion solar masses of dust formed less than 800 million years after the Big Bang. It is quite a puzzle to the formation of massive galaxies very early on, in particular the formation of dust. We've detected spiral arms and bars at galaxies at redshift 2 to 4 or so through their dust emission, which is really a new capability. And of course, I'd be remiss not to mention the fact that the highest redshift galaxies themselves have been spectroscopically confirmed through ALMA. So it mitigates the need to confirm these sources through Lyman alpha emission, or in the absence of Lyman alpha emission. It's a confirmation that indeed, some galaxies sit at redshift 9 and aren't, redshift 2 or so interlopers. And so ALMA has really been transformative for individual discoveries of testing the waters in terms of developing new techniques and studying individual systems. But the question I've been focusing on quite a lot is, what do we know about the aggregate population of obscured massive dusty galaxies, particularly at higher redshifts? And just for context, what do we know about these galaxies at low redshift? So this is an animation just showing you the evolution of the infrared luminosity function. So kind of like the bolometric luminosity function for totally obscured galaxies as a function of redshift. Two things to note about the infrared luminosity function at low redshift. There's very rapid evolution in ELF stars. So star formation rates of galaxies at redshift 2 are much higher than at redshift 0, and we see that manifest in the infrared luminosity function itself. So this is in line with what we see in the SFR stellar mass relationship, sometimes referred to as the galaxy main sequence relationship, where star formation rates are just overall much higher for galaxies in the early universe. And the second thing to note is that the faint end of the luminosity function over here is very flat. And that's in contrast with the ultraviolet luminosity function, which has a very steep faint end. And this basically tells us that dust preferentially lives in massive galaxies, which makes sense. So if we're comparing directly what we know about galaxies observable at rest frame in the rest frame UV, so Lyman break galaxies, to totally obscured galaxies, their luminosity functions would look something like this. So the Lyman break galaxy luminosity function, UV luminosity function, is very steep at the faint end and drops off as a Schechter function. And then you get the increasing contribution of more obscured systems at the very bright end in terms of when we compare their star formation rates. And Lyman break galaxies are typically 100 times more common than these highly obscured systems, but they also have star formation rates 10 or 100 times lower. And yet, so despite all of the advances in the past 10 years or so, the obscured universe is still not well characterized beyond redshift 2 to 3. So this plot shows the star formation rate density now split into direct measurements from the rest frame UV and direct measurements from reprocessed obscured emission at infrared wavelengths. And you see there are a bunch of lower limits in orange here, so we're just highly incomplete in this regime, and then we have no constraints on the infrared luminosity function beyond a redshift of 5 or so, and I think that's generous. I would say more like redshift 3, we have no constraints. And this is despite the fact that we found really extraordinarily bright systems like SBT 0311 at redshift 6.9, star formation rate of 3,000 solar masses per year, and a gas mass of 10 to the 11 solar masses. And we can't explain the dust formation in these systems really at all. So this is a a simulation, a modeling paper that tries to, form an incredible amount of dust very early on after the Big Bang. And you see, of course, a fundamental limit of these models is that you can't get a substantial amount of dust formed through AGB stars less than 500 million years after or 400 million years after a stellar population turns on. And so perhaps in the very early universe, you're forming dust more through mechanisms like supernovae. Solving how the dust forms really requires an understanding of how common these types of galaxies are. So that's what I've been focusing on, and what I'll share with you in the rest of the talk is my work to answer this question: how common highly obscure galaxies are beyond a redshift of 3. And then there are add-on questions to that, which we won't totally get to today, but I think, keep them in the back of your mind in terms of the motivation. What can they teach us about galaxy evolution and the assembly of massive halos at early epochs? And where did the dust actually come from? I think that's a rather a major unknown. So just to point out the obvious, that the primary limitation here is that solid identifications of dusty systems has been very difficult. That's what this field has been defined by over the past 20 years. And just to point out the contrast strongly, if you look at Lyman break galaxies, here's a little animation showing a redshifted LBG spectrum passing through these filters. The selection of Lyman break galaxies gives us their redshift. There's of course some contamination, but there's no question you're not going to confuse a redshift 2 Lyman break galaxy with a redshift 6 Lyman break galaxy very easily, because they break at different wavelengths. And they're also fairly common on the sky. So there are dozens per square arc minutes. And in contrast, if we zoom out, so that's the rest frame UV regime, we have quite the opposite effect going on for galaxies that are bright in the rest frame far infrared, observed millimeter wavelengths. So this is taking a fixed galaxy spectrum and pushing it back in redshift. It has fixed luminosity. And what you see, of course, is that the UV and near infrared flux densities drop like a rock as expected, and the millimeter flux density remains roughly constant with redshift. So this means that submillimeter flux densities and their colors, submillimeter colors, are often highly degenerate with redshift. So it makes it very hard to actually infer the redshift of any given system. That could be its own separate talk that I've focused on in the past. Surveys of, this is a very difficult area, because surveying dusty massive galaxies for redshifts and getting complete spectroscopic redshifts, spectroscopic completeness is very, very difficult. So the most complete sample to date comes from the South Pole Telescope SFG sample. So this is an older plot of a subsample shown here that have nice spectroscopic conformations based in the millimeter. So redshifts are hard to confirm outside of the millimeter. I've spent far too much time trying to do that in the rest frame UV through Lyman alpha telescopes like Keck and the VLT. But spectroscopic confirmation in the millimeter also requires a significant time investment from either IRAM or ALMA. So the best sample we have is about 95% complete. The second best is very very diminished in comparison. The ALES sample is 65 to 70% complete, and other samples of millimeter galaxies are only 30 to 50% complete. So what does this incompleteness mean for our constraints on the early universe in terms of obscure galaxies? It actually paints a rather dire picture. So if you consider two hypothetical universes, just a dust-rich and a very dust-poor universe. So I'm tracing out these lines as, the possible contribution of infrared luminous galaxies to the cosmic star formation rate density. Those two lines look very different and paint a very different history of the universe, and both have been claimed in the literature. And yet, the difference between these two conclusions is dependent on whether or not, 3% of a given millimeter selected sample or 7% lies above a redshift of 4. So it's really the highest redshift tail, and you have to have extreme precision on this high redshift tail to be able to infer a difference between these wildly different models. So yeah, this is what I'm calling dust poor and dust rich. It's not in reference to the dust content of individual galaxies, but overall the prevalence of these massive dusty star-forming galaxies. So an incomplete census really limits us beyond a redshift of 3. So misidentifications at a 5% level, even if you think you have spectroscopic completeness or photometric completeness, if you have photo Gs instead, can really wash out that high redshift tail. Here are just some examples of misidentifications that I'm partly responsible for, of claiming a different redshift, and then subsequent interferometric follow-up reveals that actually this millimeter source, the obscured source, is not corresponding to the galaxy for which we thought we had a redshift. And so in an effort to get to the bottom of it and figure out a way to nail down the prevalence of obscured galaxies in the first few gig years, we launched into a modeling, heavy modeling project a couple years ago that are summarized in these 2 papers, the goal of which is to synthesize all of the data to date to formulate a unified model of obscured galaxies at high redshift. So this takes advantage of all submillimeter single dish surveys dating back to 1997, and the more recent work of ALMA in terms of surveying sources at much deeper levels. Okay, the premise of the model is, a forward evolution, that we adopt some form of the infrared luminosity function as a function of redshift, and that's bolometric IR luminosity. And then for a given IR luminosity and redshift, we determine what type of dust SED the galaxy should have. We assign, a peak wavelength to it based on empirical calibrations. And then we generate a bunch of fake maps at any wavelength you'd like in the millimeter or far infrared or mid-infrared even. And we account for things like CMB, dimming, which is a dominant factor beyond a redshift of 5 or so. We degrade those maps to the appropriate beam size and RMS of realistic observations, and then extract sources and infer what we can about the population and compare that fake data to real data in order to determine whether or not the given IR luminosity function that we started out with is an adequate fit to existing data. Okay, so this model has flexibility to test multiple high redshift outcomes. What we want to do with the model is predict number counts accurately across many different wavelengths, predict redshift distributions of any IR submillimeter millimeter selection technique, reproduce cross-band flux correlations. So, if a galaxy has a certain 850 micron flux, what would it be at other wavelengths? And of course, we want it to be in line with the total cosmic infrared background, and we test both ALMA and single dish setups. Okay, what has it taught us? So these 2 models represent those dust poor and dust rich universes that I showed you a cartoon of earlier. The total IR contribution in the dust poor hypothetical universe dives like a rock here and is somewhat constant in the dust rich universe. And so the gist of all of this modeling work has told us that existing data sets cannot distinguish between even these 2 extreme different models of what's happening at redshift greater than 4. just to show you, you know, in dust rich and dust poor, we do these comparisons with both number counts and redshift distributions across different wavelengths. And then in terms of deep ALMA surveys, if you're familiar with the efforts of, you know, programs like ASPECS or Jim Dunlop's map, we simulate what those maps would look like given different histories of the universe at early times. And we find that they're more or less indistinguishable if sampled at 1 millimeter or shorter wavelengths. So how do we figure out the high redshift contribution? The key to really unlocking the obscured component, the obscured galaxies at redshift greater than 4 is to look at longer wavelengths yet. What we find in the modeling work is that 2 millimeters and 3 millimeters over somewhat, you know, moderately large areas of the sky are needed to filter out low redshift interlopers. Just as an illustration of that, here I'm showing, okay, this is what you'd see in terms of, you know, a redshift histogram of galaxies above a certain flux density, you know, in a given area of sky, relative number density for dust-rich universe versus dust-poor. And you see the peak is not at all different, and what you see, the difference is the high redshift tail. So to distinguish that high redshift tail, you really need to filter out the peak itself. So this movie is just meant to remind you of the nature of the constant flux density of some millimeter sources with redshift, the negative K correction, the very negative K correction. And that very negative K correction is even more extreme at 2 and 3 millimeters, which means that if you know, given a certain survey setup, you would not expect to find redshift 1 to 3 millimeter galaxies in a 2 millimeter survey, but you would expect to find redshift 3 and greater sources. They're brighter than lower redshift sources. So this represents something like the needle in the haystack problem of you know, typical millimeter surveys that are conducted at 1 millimeter or shorter. In that, for, you know, those surveys, you need to have something like 98% spectroscopic completeness to distinguish between these two models. Whereas if you look at the sky at 2 millimeters, you can use even simple number counts analysis. So how many galaxies are there per, you know, area on the sky, and that can distinguish between these extreme models at redshift greater than 4. And so this is what we did. We launched this survey mapping obscuration to reionization with ALMA, the MORA survey. It's a 2 millimeter deep field conducted with ALMA. It's the largest high redshift mosaic put together to date with ALMA. This is roughly about the size of a candle's footprint, if you're familiar with the candle's survey, and it's in the middle of the cosmos field. And I'm going to share some initial results of this survey. It's not yet published, but we're getting there. Just for context, if you're familiar with the other ALMA deep surveys, the ASPECS pilot, the full ASPECS program, and the GOODS ALMA survey, these are the relative sizes of those surveys compared to our 2 millimeter mosaic. I'll briefly show you a case study of the first source we found in the map, characteristics of the 2 millimeter detected sample overall, and then results of a joint analysis of both 1 millimeter, 2 millimeter, and 3 millimeter together. The first source we found in the map was not delivered to us all at once. It was, you know, came in piecemeal, and the first source we got, we were very excited about because it seemed to be consistent with a very high redshift solution. Didn't end up being as high redshift as we had hoped, but we did manage to confirm its redshift with a whopping 8 hours of ALMA DDT time last year. And that time was actually really required to confirm the redshift of the source, even though it had sat in our surveys for 10+ years without a firm identification. And so what we found is we detected a CO and a water line at redshift 5.85. This constitutes the highest redshift unlensed dusty star-forming galaxy to date. So, you know, a galaxy with star formation rate of something like 700 solar masses per year, that is not gravitationally lensed, so we can adequately estimate its volume density rather well. So it's called Mambo 9. It was initially detected with the Mambo instrument at IRAM. And this is a peek at its SED. We have very good constraints in the Raleigh Jeans tail of the SED from ALMA. It is detected with Spitzer and IRAC, and then it's an HST dark source. So undetected, this is like maybe a 1 sigma detection in one of the bands. And so this is, you know, an interesting case. You know, if you were to model its limited emission in the rest frame optical and near infrared, using 2 different models, you get dramatically different stellar mass estimates for this system, highlighting the importance of facilities like JWST to shed light on the stellar content of systems that are so extreme at early times. If you do a mass analysis of this galaxy, just by adding up everything that we can see and estimating the total halo mass, you do get into interesting territory. So given the survey volume, we actually compute, if you adopt typical, you know, the typical strategy of measuring all of the different quantities, and then if you add them up and calculate a halo mass, what you get is something rather in tension with the survey volume that we see. The galaxy would be too massive to be found in the survey overall. Now you can scale things back because, you know, there's a lot of uncertainty in things like our alpha CO or different assumptions in terms of the stellar mass. But then you get something that doesn't make quite a lot of physical sense. The dust to gas ratio is a bit too high. So you can start to use both the survey volume and constraints on what should be physical in these high mass dust enriched systems to tune measurements and get a precise estimate of things like gas mass, which you can't get in for galaxies for which you don't have a good constraint on survey volume. So we measure a gas fraction of 96% in this system. Obviously, it's, you know, a very extreme galaxy. And just to put it in context in terms of its overall halo mass, these lines here represent, you know, the limiting, the most massive halo that should be detectable, you know, in the entire sky is the dotted line, and these lines represent different survey volumes, and this black line here represents the survey volume of our 2 millimeter work. And what I want to point out here is that these halos are incredibly massive, of order the same mass as quasar host galaxies, if not more massive. And so we do have really interesting case studies for massive systems forming at very early times in dusty star-forming galaxies. Just to show you a smattering of the other galaxies detected in the survey and kind of the difficulty in identifying their redshifts, this source, so the ALMA contours, they're a little difficult to see. They're right in the middle of the frame here. We have a source at redshift 3.5. There's a complicated source, which is not super well constrained. It may also be at redshift 3.5. We have a source that has only recently been confirmed at redshift 4.6, which was mistaken as a redshift 1 source for at least 5 years. It's highly confused. We have Mambo number 9, which is this a redshift 5.85 source. It's HST dark, unconfirmed for 10 years. And then 2 more that are totally unconstrained and also HST dark. They do show up in Spitzer bands, and a graduate student of mine, Sinclair Manning, is looking into these in detail to try to constrain their redshifts. Overall, we have 12 sources in the map, which might sound small, which, you know, it is, but it's not outside of the realm of what was expected for the given area. So this shows you the expectation for dust rich and dust poor, the cumulative number of sources above a given redshift. So we find a total of 12 sources, which is in line with the dust poor universe. So, you know, beginning to really constrain that. However, the redshift distribution looks a bit different. It's more in line with the dust-rich universe. So something is not quite right about the model, and so we can go back and try to tune the parameters to understand this better. And there are a number of potential causes for this. I don't want to dwell on this. This is just where the sources lie in LIR or star formation rates. They're, you know, several hundred to several thousand solar masses per year. And most would not be detected in traditional Herschel surveys or 850 micron surveys. Where they sit in terms of the total ISM mass, so total gas mass, around 10 to the 11 solar masses. And these upper limit hashed regions show where, you know, the survey volume limits what we're able to find on the upper ends. So we're fairly well constrained between our detection limits here. And the galaxies themselves also appear to be in line with the dust temperatures of lower redshift galaxies. So this is a relationship between LIR and the peak wavelength. So that's, you know, like 1 over the dust temperature. And we see that hotter galaxies are also more luminous, and that seems to be universally true. There is some expectation from simulations work claiming that high redshift systems beyond a redshift of 5 should be much hotter given different dust compositions, but we haven't yet seen that evidence directly. Okay, and then one last joint analysis I want to present to you is that if you look at the aggregate data from our 2 millimeter map in conjunction with 1 millimeter data from like the ASPECS program, which is an ALMA large program, as well as archival 3 millimeter data, you get a conclusive picture of the presence of obscured galaxies at high redshift. So our 2 millimeter map, Jorge, this is work by Jorge Zavala, who's a postdoc in my group. A couple of years ago, he compiled archival data sets of 3 millimeter surveys from the ALMA archive, masking the intended target in the center of the field, looking for serendipitous continuum sources. And so that's a rather large survey volume, combined with the ASPECS large ALMA program at 1 millimeter. So if you take all of this data in conjunction, you can really constrain that high redshift tail, but the 2 millimeter and 3 millimeter is really crucial for that high redshift tail. So just to illustrate that point, if you look at the number counts at redshift 1, so sources at a given, above a given flux density on the sky, you get all of the gray models here represent different IR luminosity functions, and projected onto 2 and 3 millimeters, there's a huge range of potential constraints here. Whereas if you use the 2 millimeter data and 3 millimeter data together with the 1 millimeter data, it really collapses down the parameter space quite a bit. So we have, for the first time, some tight constraints on at least the integral of the IR luminosity function between redshift 4 and 8. And this is kind of the concluding plot of this work. And for the first time is directly measured at long wavelengths. So this is from Jorge's paper in PrEP, showing the total contribution of obscured emission to the cosmic star formation rate density compared to UV. And you really see this turn around redshift 4 to 5, where, you know, that's the regime where the two components are roughly matched, and above that, the rest frame UV unobscured component dominates. And this roughly is in agreement with what we see from looking at long wavelength just doing a direct assessment of the 2 millimeter sources and their contribution to the star formation rate density directly. So this is not a case where you have to integrate down the luminosity function far, again, because it's so shallow. We're just directly counting the sources we find, and that gives us insight. Okay, so I just want to, I know I have very little time left. I just want to say that, you know, so our conclusion is that these sources are very rare, but is there something to be learned from them within the first gig year of the universe? I just want to point out that we do expect massive galaxies at early times to be highly clustered. And this is relevant beyond the scope of just dusty star-forming systems. This is a plot from Yiquan Cheng's 2017 paper using the Millennium simulation to show the fraction of all of cosmic star formation contained in the progenitors of galaxy clusters. While negligible at low redshift, we see an increasing fraction at higher redshift. So at redshift 6, over 40% of all cosmic star formation sits in galaxy cluster progenitors. And of course, where star formation occurs at these early times is vitally important to our understanding of the process of reionization itself beyond a redshift of 6. And of course, this is a topic of a separate talk, but something I think is intimately related. That we, you know, big questions in this reionization era of galaxy evolution. We know that reionization ends at redshift 6 and was roughly halfway complete around redshift 7.7, as you know, told us by Planck. But we still don't know how and when it began, and if it's isolated to bubbles surrounding the most massive overdensities or more uniform, perhaps due to lower mass systems. This is a simulation, a cosmological simulation showing reionization bubbles at redshift 7 clustered around bright high mass galaxies, shared with me from Brent Robertson. And the scale of the simulation is roughly a square degree on the sky. And you know, just to point out, the existing data sets that we have giving us high redshift galaxies in this EOR, the Epoch of Reionization, right now are currently limited to much smaller areas. They don't capture entire reionization bubbles and therefore are severely limited by cosmic variance. And so if we really want to answer the question of how patchy reionization is, we need larger contiguous area surveys that are deep enough to find reionization era sources. Something like 100 new candidate redshift greater than 8 galaxies beyond the halfway point of reionization, and thousands of candidates towards the end of reionization, allowing us to map bubbles and see that indeed they would trace over dense environments. And you might think, well, we can do this with W first once it arrives, and that's certainly true, but there's a critical gap in time here that these are not yet, these surveys are obviously not yet in hand, and so we can't follow up these sources with JWST until we have them in hand. Okay, on that note, I'll summarize the talk. We have developed a model to unify the measurements of high redshift dusty galaxies as measured in the submillimeter and millimeter, with the goal of constraining how common dusty sources are beyond a redshift of 3. We've used model arguments to argue that 2 millimeter and 3 millimeter surveys are really crucial as a gateway to this early epoch. We've launched this 2 millimeter survey to constrain the infrared luminosity function beyond a redshift of 4, and we found among the sources and confirmed the highest redshift unlensed dusty star-forming galaxy to date. The real constraint here so far, which you should stay tuned for Jorge's paper, is that we've used a joint analysis of number counts to much more tightly constrain the integrated contribution of obscured galaxies to the cosmic star formation rate density beyond a redshift of 4. And do keep in mind that as massive systems, they're embedded in a highly clustered environment beyond a redshift of 4 to 6, and that as we broaden and try to study this reionization epoch in general, we do expect significant patches of overdensities and underdensities that we have to broaden our surveys to degree scales. Thank you very much.
Thank you. Thank you, Kathleen. That's very nice talk. So if you have questions, just ask in the chat. Maybe I can ask the first question. When you showed the plot you have here on this slide where you combine